Welcome to the second part of the virtual laboratory demonstration on fluid mechanics. We have seen the laboratory demonstration in the virtual mode in the first two experiments in the previous lecture, where we talked about to determine the loss variables for different types of flow in pipe and open channels. That is, we talked about the Reynolds number determination to find the behavior or the types of the flow. Then also we talked about variable area duct verifying Bernoulli's energy equation. These were a few experiments which were on the theory of the fluid mechanics. In this lecture, I will talk about pumps and turbines, more focus. First, I will start with gear pump. You see the experiment number 8 is here, drawing the characteristic curves of gear pump. I will click this. It shows the aim as to study the performance of a gear pump and draw its operating characteristics. In the theory, we have the gear pump as you have already seen in the lectures. There are kinds of gear pump, a gear pump cross-sectional view where from the one side the inlet is here, the fluid is coming, the gear will rotate to make the fluid pass through this periphery and pass through, that is the outlet side. So, this was already invented in the year 1600, but a lot of updates kept on coming. It is considered one of the most important positive displacement pump, that is the rotary pump. In general, it encloses a fixed volume of fluid with help of interlocking cogs or meshing of gears that applies mechanical force and pressure. So, parts of gear pump could be, there is a driver gear, there is a driven gear, there is a casing. Casing is important so that the fluid or the oil, whatever we are trying to pass through it, does not splash out. So, clearance is provided between the gear and the casing so that the fluid passes through this periphery properly. So, there is a low pressure fluid on the left side, on the right side in the outlet you could see the high pressure fluid. When we say pump, like heat pump we talked about, gear pump is also where from the low pressure to high pressure it will be having a transformation. Now, there are always safety valves in the gear pump. Safety valve or release valve are installed on the discharge side so that the pump can be protected from being damaged if additional pressure arises when it is released. Because it is positive displacement pump, there could be no flow back. So, that is why safety valve is always there to release the pressure if it is above the threshold. You see here the fluid enters, the pump gears, driver gear and the driver gear both are rotating, and it passes through this casing periphery, inside periphery of the casing, and it goes as an outlet discharge. So, this is gear pump. We have talked about internal gear pump. This is the internal gear pump where we have an idler gear inside and we rotor. There is kind of an internal gear pump. External gear pump is a very generic pump that we have shown in the above figures as well. So, to talk about the gear pump, let us try to see a few pre-test questions so that we see are we ready for taking the simulation experiments. A few pre-test questions. The first question is gear pump uses what? Pistons, buckets, meshing of gears, crankshaft. It uses meshing of gears. Fundamental significance of all the turbo machinery is momentum conservation. It is not heat, mass or energy, it is momentum conservation because we are talking about turbo machinery here. Most widely used pump for viscous fluid is gear pump. Gear pump is a positive displacement pump, like we have discussed in basics of mechanical engineering 1. We talked about the types of the gears. There were belt drives, there were chain drives, there were gain drives. When gear drives were used, gear drives are always positive, and those are also for the heavy power transmission. So, now here as well the gear pump are used when the viscous fluid is there and there is large force required to transfer the fluid at a higher velocity or higher pressure. Gear pumps are mainly used in chemical installation because they pump. So, amongst high density and high viscous, I will try to pick high viscous liquid is the right answer. Suction is created in the gear pump due to low pressure from the inlet side. Gear pump is tangential flow pumps, submersible pump, positive displacement pump, negative displacement pump. It is a positive displacement pump. That is the first statement I made when I talked about the gear pumps. Gear pump has dash discharge, 0 pulsating, sinusoidal, intermittent, linear. It has zero pulsating discharge, and these primarily transfer pressure, speed, fluid, power. Fluid is the most appropriate answer here. Gear pump does not require priming. Yes, it is true. At the inlet of gear pump, suction pressure is created by, at the inlet, the suction pressure is created by the rotation of gears itself. Let me submit. I got 10 out of 10. That means we are ready for the simulation. Let me see the procedure of the simulation. They say ensure the complete open position of delivery valve, measure the height of pressure gauge above the vacuum gauge, switch on the pump, vary the flow rate that is discharged by closing the delivery valve, adjust the delivery valve accordingly, the pressure gauge reading of 1 kg per centimeter square, note down the vacuum gauge's reading, note down time taken, that is for h centimeter rise of the oil. 10 centimeter is the graduated scale that is there in the setup of the experiment that I will show in the next page here. Note down the time taken for n revolutions of energy meters. So, they have taken 3 revolutions here. Repeat the procedure of 1 kg per centimeter square incremental by closing the delivery valve gradually for 1.0, 1.5, 2.0, 2.5 and 3 kg per centimeter squares, and switch off the power and delivery completely. Then we note down the readings. So, these are certain relations which are used to calculate the total head. Total head is given by H is equal to P plus V by 760 into 10 raised to power 5 by rho g plus z. So, this is P pressure gauge reading, and V by 760 is also there because we are talking about mercury here. Then we have discharge, which is A into H by T, that is total volume per unit time, area into height, the rise at to which the water rises. It is 10 centimeters, that is 0.1 meters. Output power is rho g q h by 1000, and an input power is given as N into 3600 into eta by EC into T, where N is number of revolutions taken in an energy meter, that is 3. Eta is efficiency of the motor. This efficiency of the motor is given, that is 0.8. Then we have efficiency, that is output per unit input. Let me come to the simulation. So, this is a similar interface that we have been observing from the previous experiments for the Reynolds numbers determination experiment, and for the Bernoulli's this kind of setup was even there. Now, here it is a setup specifically for the gear pump. You can see here we have a gear pump, 2 mirrors are meshed here, and when we switch on the power, because it is oil, the color is brown, the oil is flowing through the pipe and it stops till the gate valve. Then we can position the gate valve amongst 1, 2, 3, 4. Let me keep it at position 1 first, and it is opened. Now, the oil starts entering the tank and it is also discharging out through the discharge valve. I have to close the discharge valve, that is also an instruction here, taking it of the vacuum pressure gauge reading and pressure gauge reading, and then close the discharge valve using close discharge valve button. So, I click on this. So, fluid is filled till 10 centimeter height of the tank and time taken is 19 seconds. Now, vacuum pressure gauge reading is 160 millimeters of mercury and pressure gauge reading is 0.5 kg per centimeter square. It is the valve position 1. Now, I will start the electric meter for the gear to pump. A number of revolutions would be 3. For 3 revolutions, it took 28 seconds. All these readings would be noted down here in the observation table. The pressure and vacuum gauge pressure, both of them, the pressure is 0.5, vacuum gauge pressure is 160, Z, that is in meters, in 0.3, time for 10 centimeter rise of water, that was 19 seconds, and for 3 revolutions the time taken was 28 seconds. All these observations are noted here. Now, let me bring it to another position, in the second position. I have to close the discharge valve. Now, the time taken is 20 seconds and pressure gauge reading is 1 and vacuum pressure reading stays as 160 millimeters of mercury. I will start the electric meter for 3 revolutions, revolution 1, revolution 2 and revolution 3. The time is 27 seconds. I will note these readings as well. This time this pressure is 1, this stays as 160, this is 0.3 and this value of Z is given here, datum head is 0.3 meter. Time taken is 20 seconds for filling the tank till 10 centimeter height, and for the 3 revolutions the time taken is 27 seconds. Now at the third position, closing the discharge valve, 20 seconds again, but this is at the pressure of 1.5 kg per centimeter square. Starting the electric meter for 3 revolutions, that is rotating the gas. For 3 revolutions, the time is 26 seconds. So let me note down the readings here. It is 1.5, 160, 0.3. Again it was 20 seconds to fill till 10 centimeter of the water or oil. Then comes for 3 revolutions, it was 26 seconds. Now at the fourth position, again running the electric meter for 3 revolutions. So 21 seconds for filling the tank, 21 seconds for 3 revolutions and at 2 kg per centimeter square of the gauge pressure. So here it is 2 kilograms per centimeter square, here it is 160 millimeters of mercury, Z stays as 0.3, this time is 21 seconds and for 3 revolution also the time is 21 seconds. Now comes the calculation table, total head, flow rate, input power, output power, efficiency is to be calculated using these relations. Total head is equal to P plus V by 760 into 10 to the power 5 by rho G plus Z, and Q, that is discharge or the flow rate, is in meters cube per second, is area into height per unit time. Then we have output power, that is rho G QH, input power as N36 eta by E into T, and efficiency would be output power per unit input power into 100. To do this, I will again export this to Excel, and I have already developed an Excel sheet for you. To save on time, I have entered all the values of the observation table here. These are the values that we have taken or seen in the virtual laboratory demonstration. Now for the first value, that is for 0.5 kg per centimeter square of the pressure, and for these times 19 seconds and 28 seconds for filling of the water or oil and for 3 revolutions respectively, I have put the formulas here. What was H? H was this formula, you could see. It was P plus V by 760 into 10 to the power 5 by rho G. All the values are entered in this formula. You could see B4 is P, pressure, C4 by 760 is V by 760, then this into 100,000 by 860 into 9.81. So what is this? 860 is the density of oil, it is rho, into G plus Z. Z is 0.3. So this is the value of the head, total head that is gotten. Then for the flow rate, the formula is given, which is given here, that is A into H by T. Area would be what? 0.3 into 0.3, that is given, into height is 0.1, that is entered here, 0.3 into 0.3 into 0.1 by time taken. Time taken is 19 seconds. This is the value that is given in the cell E4, that is entered here. So this gives me the flow rate. Then comes input power. Input power relationship that was given here was N3600 into eta by E into T. This is also put here. N is 3 revolutions, 3600 into eta is 0.8 by E into the time that is given in cell F4. So, you can see here that energy meter constant, that is EC, is 1200 and time taken is for the specific observation. Eta, that is efficiency of motor, is 0.8. All these values are entered here. 0.8 is the efficiency of the motor, 1200 is the energy meter constant. So, this gives me the value of the input power. For output power, we have rho GQ into H. So, this is rho 860 into G 9.81 into Q. Q is calculated here in the cell E12 into H. H is also calculated here in the cell B12. The formula is given. Efficiency is simply the ratio of cell E12 by G12 into 100. We have gotten this efficiency. I have also taken all these readings for the observation number 2, observation number 3 and observation number 4 for these 3 observations. So, let me show you all the readings here. So, these are the readings and efficiency that is shown at the valve position. In the first position it is 13.555, for the second position 20.8, for the third position it is 28.207 and for the fourth position it is 27.948. I have put exact value which are given in the provided data, it is given data and in these formulas and exact observation. Now, let me suppose I put all the values here and calculate, then it will show me the results. I can input all the values here. Or there is another quick way if you are not able to reach the final calculations, because you put any values, it will show the value is not correct, but it will show you the result. For that, I am just demonstrating you how do you do that, though it is not a correct way. I am putting some value, maybe I will put value 1 in each of the cells here. So that at least some data is entered. And if suppose you have missed something in some formula, you are not able to calculate, then when the values are added, I will calculate it and it will calculate efficiency. Then we can see the result. This is the result. Now, we will all of the values are given red here. So, that means values are not correct, but this is the calculated value. So, this is efficiency, also the same efficiency that I have calculated in my result here. You see, these values are given 8.7220, exactly this value is calculated here. I have shown you the formulas here as well of all the values here. We could do manual calculation, we could do calculations using this. So, this is the simulation. Now, let me come to the post test questions. It says flow rate in gear pump remains constant with increase in pressure, decreases with increase in pressure, increases with increase in pressure, increases with decrease in pressure and is unpredictable. The answer is it remains constant with increase in pressure. Positive displacement pump work on this principle. What is the principle? Liquid has dynamic action, liquid is discharged due to the positive displacement. Yes, this is the correct answer. Which one of the following is not a positive displacement pump? Vane pump, gear pump, centrifugal pump, screw pump. Centrifugal pump is not a positive displacement pump. Then next question is, gear pump is more suitable to pump. It is more suitable to pump viscous fluids amongst air, hydrogen, water and paint. Paint is the most viscous fluid. Rotation of gears in internal gear pump is in independent of each other, opposite direction, same direction. It is in the same direction when we talk about internal gear pump. Rotation of gears in external gear pump. In external gear pump, the rotation is in opposite direction. Internal leakage in the internal gear pump is caused due to, the answer is more tolerance level between the meshing surfaces. Relationship between the pressure and overall efficiency of a gear pump is pressure increases when overall efficiency decreases. Continuous discharge of liquid is achieved in a gear pump by, when we say continuous discharge, it is always a positive displacement pump, but the discharge could be discrete at some points. To have a continuous discharge, we can have more number of teeth. So, here the answer could be by increasing the number of teeth. How does the fluid flow in internal gear pump? The fluid enters the suction side between rotor, which is a large exterior gear. So, I think answer is C here. Fluid enters the suction side between rotor, which is a large exterior gear, and idler, which is a small interior gear. Let me submit. All of them are correct. Let me see the explanation. To internal leakage in air compressed gas due to the more tolerance level between meshing gears. Internal leakage occurs when there is excessive clearance or tolerance between gears and the housing, allowing fluid to leak back and reduce the efficiency of the pump. That is, if there is a gap or the clearance between casing and the rotating gear, if this is high, internal leakage could also happen. So, with this, the gear pump experiment is complete. So, next is reciprocating pump, that is experiment number 7. Characteristic curve of reciprocating pump. To perform a characteristic of single acting reciprocating pump is the aim here to study the performance and draw a characteristic curve. Reciprocating pump, now you know, it is discussed in the theory. It is a reciprocating motion, that is, it is sucking from one side and trying to pump to the discharge side. It could be single acting, it could be the double acting pump. Double acting pump has double the efficiency of the single acting pump. How? Let us see parts of the reciprocating pump. We have the suction pipe through which water or fluid is sucked here, and the piston, when it goes back, it is, let me say, if it is IDC, that is inner dead center, and this is ODC, that is outer dead center. At IDC, the water is not there. When it goes towards the ODC, when it goes towards the right side, the valve here at the suction point opens and water starts coming in, and when it is coming from the ODC towards the IDC, that is from the outer dead center to the inner dead center, the water goes out through the delivery pipe. This is the valve that opens as well here. So, here is the head difference HS and HD. HS is for suction, HD is for discharge. We have delivery pipe, we call it discharge or delivery. There is a piston rod, there is a crank to run the piston, and there is a cylinder in which the piston is being reciprocated. So, there are components, as you see, cylinder, suction pipe, delivery pipe, suction valve, delivery valve, piston and piston rod, crank and connecting rod, strainer and air vessels. So, these are all components which are explained. So, this is air vessels in reciprocating pump. There are air vessels in which reciprocating pump has an application. So, difference between single acting and double acting pump is there. In single acting pump, you see the fluid is delivered during the delivery stroke only, that is when the crank angle is between 180 to 360 degrees, only then the delivery of the fluid is there. Rest part is only suction, that is, this time is completely wasted. That is why we use double acting pump as well, in which in both the strokes, that is inward or outward stroke, the delivery is happening in suction and the delivery stroke both. How? See, this is delivery during the single acting pump that I have shown you. In double acting pump, we have both the sides suction pipes and the discharge pipes or delivery pipes. So, both the ways, even if the piston goes from left to right or right to left, the discharge is happening. That is why you see this is the discharge, how it is happening here. So, this is QD, the discharge rate. So, there are multiple applications of the double acting reciprocating pump. Now, let me see the pre-test questions. The first question says, a reciprocating pump is used when there is low volume of liquid is large, pumping high pressure, pumping low pressure. When there is low volume of liquid, only then reciprocating. Second question, positive displacement pumps are also called as dash pumps, constant volume, constant heat flux, constant pressure, constant head. These are called as constant pressure pumps. Daily life example of a single acting reciprocating pump is a syringe. Power operating pump in which both sides are engaged in fluid displacement is known as centrifugal, double acting, single acting, bicycle. It is double acting pump. Power operated pump in which one side is engaged in fluid displacement is known as single acting pump. When the piston moves forward, the liquid draws into the cylinder. Rotary motion of the motor is converted into translator motion of the piston through plunger, crank, suction pipe or delivery pipe through crank. Following are the advantages of reciprocating pump: high pressure, low volume applications, durability, all of these are the advantages. An up and down, back and forth translator motion is called. Examples of reciprocating pumps include bicycle pump, hand pump, axial piston pump. All of these are reciprocating pumps. Let me submit. I have gotten everything correct. Now, let me come to the procedure. They say note down the diameter and stroke length of the piston, water meter constant K, distances Z, D and ZS of the pressure gauges from the pump axis. Start the motor and open the delivery valve fully. Measure the discharge Q actual, note down the pressure gauge readings, that is PD and PS, that is for delivery end, for the suction, and also watt meter reading X. Measure the number of strokes occurring in a given time and hence obtain speed of the piston in RPM. Change the opening of delivery valve. Repeat the steps 3 to 6, that is measure the discharge, note down the pressure readings PD and PS, measure the strokes and change the opening. Then these are the relations which are used. Theoretical, the value of Q is A into L into N by 60 plus A minus A into L into N by 60, where L is the length of the stroke, N is the speed of the crank pin, and small is the cross section of the piston rod. Capital A is the cross section of the piston. This is theoretical. We will have a practical formula that is given in the simulation. Here, this is a setup in which we have Q is equal to A into H by T. P input is 3.6 into 10 into N into 1.36 by K into T revolution. P output is W into Q into H, and eta is the output power by input power. Now, let me run the experiment. Switch on the power first. It has started, reciprocation has started. You so know the fluid is coming here. Valve position at position 1. Now, it says close the gate valve. It is very similar to what we have been doing. Now, the fluid is filled till 10 centimeter of height. Now, for 10 revolutions, we will start the electric motor. It is showing 460 RPM, 0.46 kg per centimeter square of the pressure gauge reading, 0 kg meter per centimeter square for the vacuum gauge. Time to fill the tank till 10 centimeter of height is 32 seconds. Now, let me start the electric meter. It will run for 10 revolutions. The time is 50 seconds. All these observations should be now noted in the observation table. You can note down on a paper. I have also noted down on a paper pressure, vacuum gauge pressure, time to fill 10 centimeter for 10 revolutions, and speed in RPM. This value pressure is 0.46. For the vacuum gauge, the pressure was 0. Time to fill this is 32 seconds till 10 centimeter of height, and for 10 revolutions the time taken was 50 seconds, and speed is given as 460 RPM. This speed will remain constant because it is a reciprocating pump which works at a constant speed. RPM will stay constant here. Now, let me see at a second position of the valve what is the opening. Now, I will close the gate valve. Now, it took 33 seconds, and for 10 revolutions it will run. I will by this time note down 0.42 and 1.0. 0.42 and 1.0, and it took 33 seconds and 43 seconds respectively for both the water system running. Now, valve position at the third point, water is going in, entering the tank, closing the gate valve, water is now filling up. It took 35 seconds. I will run this for 10 revolutions. I will note down the readings 0.42, 2.0 and 35 seconds. 2.0 and it took 35 seconds. So, what the time taken here for 10 revolutions is 37 seconds. Now at position 4, it is running here, closing the gate valve. It is 0.38 of the pressure gauge reading, 3.0 vacuum gauge reading, 36 seconds of filling the tank till 10 centimeters. 0.38, 3.0 of vacuum gauge reading in kg per centimeter square, and it took 36 seconds, and next it took 29 seconds for 10 revolutions. The last position of the valve, closing the gate valve, it took 37 seconds, and I will start the meter. 37 seconds, pressure gauge rating as 0.4 and vacuum gauge as 3.5, time for 10 revolution is 31 seconds. Putting all these values here, it was 3.5 kg per centimeter square of the vacuum gauge pressure. Time it took was 37 seconds here. It took 31 seconds for 10 revolutions, and observation table is now ready. Now we need to calculate the head, flow rate, input power, output power and efficiency. For all these we can use these formulas, we can put all these formulas there and try to calculate. It is a straightforward thing, putting all these values here. I will quickly do the Q and power input for you. Here Q is A into H into T. To do this, we have area given 0.25, H here is 10 centimeter, that is 0.1 meters, and T, that is time taken, is 32 seconds for the first experiment, and for input power it is given 3.6 into 10 into N into 1.6, and here are 10 revolutions it has taken. K is given, K is energy meter constant 15.018, and time taken for revolution. Quickly putting this here, we have Q is equal to A into H by time, that is area given is 0.25 meters into H is 10 centimeter, that is 0.1 meter, by time taken is 32 seconds. When I calculated this, this came out as 0.000781 meter cubes per second. This is for the reciprocating pump. It is single acting. And when I say input power, this is equal to 3.6 into, it gives the formula as 10 into number of revolutions into 1.36 by K into time for the revolutions. Here K is given and N is given. Putting the values 3.6 into 10 into 10 into 1.36 by value of K is 15.018 into time it took was 50 seconds. This value turns out to be 0.6520 horsepower. Similarly, I am just saving time. You can calculate the output power and you can calculate the efficiency. You can calculate and put it here. I have calculated everything and I will just put the values in the observation table. Total head calculated here is 4.6. Total head calculation is little vast. Total head can be calculated using the formula that is given in the procedure here. You can see the total head here is using this pressure and volume. This you have already done in the previous experiment. I will just enter the values here. Flow rate that we have calculated is 0.000781. input horsepower we have calculated is 0.6520. Output power that is calculated is using this relation W into Q into H by 75, where W is weight of the water 1000, Q is that one we have calculated 0.000781, H is the total head, that is 4.6 here. We calculated the output power as 0.0479. This gave me the efficiency of around 7.349 only. This was for the first observation. For the second, third, fourth and fifth observation, you can take the values, put the values, and then you can draw the characteristic curve, plotting the efficiency based upon the Q, plotting the efficiency based upon the head. This you can plot here, and to see the values, I have already calculated all of the values. I will just put it here. It is 14.2 here. This is 0.00075, and this is input power is calculated as 0.7582. Output power is calculated as 0.1434. Efficiency is calculated as 18.9. I will put all the values, then click the word calculate. Now, I have entered all the values. Let me click the button calculate. Efficiency is calculated. Let me see the results. So, see, the results are very similar. They have shown few values as not correct, which are there in the red color font. So, the values are very close. Anyway, they are showing not correct because these are till very large decimal place. Efficiency what I have calculated is 33.40 for the last observation. Here it is 33.410. Only then it is showing this value. Otherwise, the values are almost all correct. It is correct to the less than 1% of accuracy. So, this was the single acting experiment simulation. Let me see the post test questions. Amount of fluid that leaks from a higher pressure discharge to a low pressure discharge is called, this is called slip, because it is from high pressure discharge to a low pressure discharge. It is slip that is happening. On which of the following parameters the slip in a pump majorly depends? It majorly depends upon the wear that is there in the pump. If slip exceeds 5%, the pump needs to be dragged, intermittent, serviced or dumped. If slip is more than 5%, the pump is required to be serviced. Maximum efficiency of reciprocating pump is, in a reciprocating pump, maximum efficiency goes up to 85%. For a good condition, slip should be, whatever the minimum value is, I will put it here, it should be below than 2%. Reciprocating pumps have dash efficiency compared to centrifugal pumps. It has lower efficiency when we compare to centrifugal pumps. Which of the following are the beneficial effects of air vessel fitted to delivery side of a reciprocating pump? Ensures constant rate of discharge, reduction in power consumption, increase in discharge. Here, ensuring constant rate of discharge, reduction in power consumption, these two are correct. Increase in discharge does not hold good. The dash of a double acting reciprocating pump as compared to the single acting pump will almost be double. What is double? When we try to compare a double acting reciprocating pump to a single acting reciprocating pump, we double the flow output. The typical work saved by fitting an air vessel to a single acting reciprocating pump is So, typical work that is saved is 85% because we are talking about the efficiency. Discharge of a double acting reciprocating pump is where L is equal to length of the stroke, A is equal to cross section area of the piston, N is equal to speed of the crank. Here the discharge is 2 times length into area into number of rotations by 60. This is 2 LAN by 60. Let me submit. It shows discharge is this. So, that is the factor of 2 accounts for double action because we are talking about double acting reciprocating pump. Had it been single acting, answer would have been L into A into L by 60, B could have been answer, but now the correct answer is 2 times length into area into the rotation speed by 60. By 60 is always added because when we talk about N is in RPM, rotations per minute. To convert minutes into seconds, we always divide by 60. That is why it is L2 LAN by 60. Now, with this I have completed the pumps part. Here we have talked about the 2 types of pumps. We have talked about reciprocating pump, single acting reciprocating pump, we have talked about the gear pump. In the next lecture, I will try to talk about the turbines. I will take majorly Francis turbine, which is most widely used turbine, and I will also take before that a Pelton wheel or Pelton turbine. We will try to see how do these work. Thank you.